Howdy, everyone. You guys can't
Howdy.
unmute yourself, but I can see that you're waving and saying hi.
I can unmute myself.
Well, you have special powers.
I've got the power.
Yeah.
I'll even keep my video on so you can talk to a face.
Yeah, thank you. Chris with no last name must be Nevers. So I think we're just waiting for Dan. Nevers. This is going to be a very no holds barred walkthrough of things. Is the font size okay, or would people like it bigger? It's okay. Is that an okay Ryan or a bigger? PB's here.
It's a bigger.
It's a bigger.
Yeah.
Okay. I made it a little bit bigger, Russ. Do you want me to? That's good. Okay, good, awesome. Okay, so my plan is to basically walk through how one simple program gets compiled, to just use that to demonstrate how things happen underneath the hood. And I'm not going to talk about the entire compilation process. We're basically going to go from the reach program to what's referred to as the projected language. So overall, the way that reach works is that your input program is basically evaluated statically in a JavaScript-like environment where we basically it's kind of like partial evaluation, where the residual program that's left over are the variables that cannot be known statically, and instead are ones that can only be known when the program actually runs for the real time. So essentially we have like a evaluation is compilation model. So an example would be something like what we call the interact function. So interact, really the way that I think about that is it's like an argument that will be provided in the future. And so because of that, we don't know exactly what request is or what info is. We just know that it's some number. And that means that the whole rest of the program basically will be, like I said, residualized around this value. And so, for instance, if we were to do something like do request +1, then we're not going to really add the number now. Instead, what we're going to do is we're going to record that in the future we should add a number. So as we essentially run the program, and we have these symbolic variables that represent things that will appear in the future. That's sort of like the first stage of compilation. Then the next thing we do is we like figure out what the control flow graph is. And here, when I say control flow graph, I don't actually mean a control flow graph in the same way as normal programs. I specifically am interested in the control flow graph with respect to the communication network. So in this program, it's trivial because A does something, and then B does something, and then A does something, and then we're done. So it has a straight line communication. So essentially what we're interested in is what are the times that we have to go to the network and what is the control flow graph of those? So for instance, do we do two things and we enter a loop where we keep coming back to the same state? Because what we're trying to do is trying to figure out what transitions there are inside of the smart contract state. Because when you write a reach program, you don't say anywhere what the smart contract is. We derive that. And so the way that we derive that is by observing the actual state transitions of your program and then working back from that to say, okay, well, that means there must be a variable that says we're in this state or that one. Then once we've figured out what the control flow is, then essentially what we do is we take slices of the program that correspond to each participant. So we take a slice corresponding to what Alice is, a slice corresponding to what Bob is. And when I use the word slice, I actually am referring to a normal programming language analysis tool, which is called program slicing. And so we slice from the perspective of a role. My dissertation calls this endpoint projection. And it's basically, you can kind of think of it as like our program is like a strand of DNA where there are pieces that Alice does and there are pieces that Bob does, and the program includes all of them. And so what we do is we separate them. So because Alice right here publishes, that means that we know that Bob must receive. And Bob here pays, and pay is kind of like publishing. That means that we know that Alice must receive there. And so from every line that is in the combined program, we can figure out what would have been on the other side, and we can separate them. Similarly, we're actually not separating only two things, we're separating an arbitrary number of things, and we're separating an arbitrary number of things plus we're figuring out what the contract state is behind the scenes. The output of that, that's what we call the projected language. So let me just open up another thing. So that projected language, it's described by this really simple data structure that's called a CP, a C program. C stands for contract program. So a contract program, basically what it's going to do is it has a mapping called handlers. And what handlers is it says, step number 0 of this program is this code, step number 1 is this other code. And steps can either be handlers, which correspond to publishing events, or they can be loops. Loops are there when we have while loops. Every handler says when it is allowed to be called, and this is relative to the last time that an event happened on chain. It binds a variable called from, which is whoever sent this message. It also records what handler it expects to be called from. So basically it has its parent in the control flow graph. It then records what it expects the environment of the previous one to have saved for it. So this is kind of like the variables that it reads from. So if we're thinking about a control flow graph, this is the read set. And then the message, this is the arguments to it. This is what will be provided by the client. And so that basically corresponds to what is the publication in the program. So for instance, in this first step, that message would be this request. And for B right here, message would be empty because it's not publishing anything. And here it would be info. And then time V is a binding. It binds the current time to be that variable. And then the body is a CTAL. Loops.
Hey, Jay.
Yeah.
Before you go on, I just turned on chat so people could ask questions.
Okay, great. Let me make it so that make sure I see that the chat is actually open for me. Okay, so I now have it actually open so I can see. Okay. Loops are very similar because they say what variables what's their read set is, and what they receive as arguments. And these variables are essentially what the loop variables are, what are modified by the loop, and they have their body. And what tails are either one of the many what are called common statements that are basically the things that are preserved across the entire reach program. So this is things like addition and whatnot. There can be if statements, there can be switches, and then you can end in either a from or a jump. A jump means that you're going to a loop. So you're saying, I want to jump to this loop, and I want to run this code right here. Sorry, and these are the saved variables that I am providing to it. And then here is my assignment of its loop variables. So this is sort of like you're passing it along your state, and here's its arguments. And then what CT from is, that means that I am stopping, this program is over, and I'm going to save my state onto the chain so that in the future it can be picked up. And this from info, essentially what it has in it are the saved variables for all of its children. So in the control flow graph, it has a bunch of children, which are the next things that could happen. And so that from is saving all of their variables. Yeah. Okay, so that's what this data structure actually is. Now, we can see these variables by looking at the output of the reach compiler. So if we look for something like, if we look at this message right here, where it says B pay request, then that's going to be inside of the Bob portion of the code. And it's going to be right here. So right there, it says send receive, and it's sending to 2. And so 2 means it's message number 2. And it is sending V24, 25, and 27. And there's no arguments either. So this basically says there's no message. And then this V25 is how much money is being sent. And so this right here is basically a call to a handler at step 2. I think what I'm going to do is I'm going to open up the actual compiled version of this so we can see. I'll just go down here. Okay. Yeah, so this is decent. Okay, so if we were to look at this, then like right here, we can see that step 2, what it does is its last time is I don't know, that's not the last time. That is the, what is that? What is that 31? I forget what that 31 is. This between right here, that's the interval. This is the last time. This is the last. These right here are the saved variables. These are the types of those things. And then these are this is the message, then their types. This is the time variable that gets bound. And then this is the actual body of the code. So it does a check pay, which is one of these common things, and then it immediately saves. So I of course haven't actually showed you the compiler yet, but just sort of talking about what it gets to look at. Now, one of the things that's going to happen is that the Algorand code is going to need to know what the final state of the program is. Because this from right here, where it saves stuff, we actually have to deliver that to the program. And this is a detail of how we compile. And so because of that, in our JavaScript, we actually have a simulation right here. That's what this code is. This is a JavaScript simulation of what the Algorand program will actually do. And so what it's going to do is it's going to say, well, my previous state had better be this. And Then what I'm going to do is I'm going to record that this transaction must happen. This transaction right here is basically saying there should be a transaction that is to me that is the amount of 25. That is this check pay right here, where it says that I need to check to make sure that I have been paid 25 units, or the whatever is in 25. I need to check that. Then my next state will be this, and then this is not a halt. So that means that the program is not over because it ends in a from where there's actually something next. It's not, see it says continue right here. That means that we're going to another thing after this. So this simulation right here is really part of the Algorand compiler. We're only doing it because of how the Algorand thing works. But it's really implemented by the JavaScript. And essentially what's going on here is that this previous state, it is a digest of our saved variables, 24, 25, 27, plus, see how it says the number 1, that number 1 is this number last right here. So we're basically saying that the previous state had better be 1, 25, 24, 25, 27, and then at the end, when we say what our next state is, this is annoying, I'm going to turn this off. What our next state is when we're done, we're going to say that now the state is 2, 24, 25, and 34. So I guess we don't need 27 anymore. We now need 34. Okay. So with that kind of framework in mind, I'm actually going to fast forward to where the launching actually happens so we can see some of the details that are going to show up in the compiler later. So what we're going to do is that then we're going to look over here at this side. Let's split this and look at backend. Okay, so the compilation is going to output these things right here. It's going to output an approval program 0, an approval program, a clear program, an escrow contract program, and then an array of programs corresponding to each step of the program. So for instance, this right here is the approval program. Then this right here is the approval program 0. This right here is the clear program. This right here is the escrow program. And then there are 3 steps of this program. This is step 1. And then going down. Well, I guess I actually missed the separation between the steps. So let's go. Yeah, so there's just going to be all right, here's what we're going to search for handler. Okay, so here's number 2. So here's the, so we want handler space. Okay, so this is the first one, then there's the second one, and then there's the third one. So they're all inside here. Okay, now what is the point of all of these? What is the point of the different ones? We'll go down to deploy, where it happens, just right here. Okay, so here's how the process works. We go off and we read the compilation output, and we get back the approval program 0 and the clear program. We figure out who we are the deployer. And what we're going to do is we're going to replace a template variable inside of the approval program 0, which I guess I'll load over here so we can see it. We're going to replace this variable in the program with us. What are we doing? What we're doing is we're making it so that this approval program, the only thing that it is allowed to do is update itself, update the code, and we are allowed to update the code. Why do we need to update the code? The reason that we need to update the code is because we don't know what number this application will be given. Because on Algorand, when you launch an application, it gets given a number, so like 5 or something like that. And so we need to know what that is, but we also need to, and we're gonna take that number 5 and we're gonna embed it in each one of these steps right here. And then we're going to take those steps and we're going to embed those inside of our application code. So basically there's this self-referential thing where we need to start it somewhere. And so we're going to start it by launching the application, getting the number, and then we'll go fill in all the other details later. Okay, so we go off and we do this substitution, and then we go and we actually compile the teal program, because it like literally takes the string, replaces it, and then sends it to the algod node, compiles it, and gets the compilation output. We also compile the clear program, which we know it always is the same. Then what we're going to do is we're going to actually create the request, create the application, make sure that the creation happened, and now we've learned the application ID. At this point, we can now do what's called compile for. So what does compile for do? So what compile for does is it says, well, I know who the application ID is, and I know who the deployer is. So what I'm going to go do is I'm going to go and I'm going to substitute the application ID and the deployer into all of the other contracts. So I'm going to go and I'm going to say, okay, well, let's look at the escrow contract and inject into it what application it is and inject into it who the creator is. So if we go look at the contract right here, see it says that I had better be in a transaction group where the first transaction, its application ID, is the one that I know about. So this escrow account, it basically, this is the entire thing right here. This escrow account, it knows that it can only be called when the first application is this application. So it injects itself in. Then what we're going to do is we now know the identity of the contract address, because we're going to, one of the things you can do in Algorand is you can take a program that you've compiled, and every program simply is an account. And so since it is an account, that means that it just exists out there and you can transfer money to it. So the account that corresponds to this code is the escrow account. Now that means that if the same application ID ever got allocated twice, you know what I mean, then that means that they would all share the same escrow account. But we know that Algorand doesn't give them out twice, so it's going to be this one because they're unique. So that means, so this right here is the escrow account for this application. Okay, so the next what happens is now that we know what the escrow account is, we can then go through each one of the steps and go inside of it, and we can substitute in the application ID, the contract identifier, and the creator. So if we were to go look inside of each one of these steps, it's going to embed in it, am I part of the application? And then it's also going to say somewhere in it, did I receive funds? Is the receiver of the third message, is that the contract account? Did you actually send money to the escrow account associated with this application? And then sometimes it'll mention the deployer. So we've now injected that in, and we're going to go compile that. And we always check to make sure that it's a valid program. So we check to make sure that its length is reasonable and that its argument count and length are reasonable. The reason that we can't do this beforehand is we don't know how long the output's going to be, because we don't know which variable is going to, which constants are going to be optimized. We don't know which ones, we don't know what bytes these are going to be. No, I mean, we could probably know that the contract ID is going to be 32 bytes or something like that. So maybe we could actually kind of do this check beforehand, but we don't. We wait until do it now. So then once we've compiled every single one of the steps, then what we do is we actually go back, and now what we're going to do is we're going to go and take all the addresses of those steps. And those steps, by the way, are also going to be these logic accounts. So they're going to be accounts that are just this logic signature. So they don't exist. It's not like we create an account and then we use that account to sign this program. The program itself is the account. So they don't exist for any purpose other than to like just be this code. And they're not going to hold any money either. One of the tricks that we're going to do is we're going to make it so that when we want to get one to run, we're going to transfer into it a minimum balance. Then we're going to get it to transfer to us 0 and close its account to us. So what that's going to do is it's going to make it so that it is allowed to do something because it has a minimum balance for that one frame, one round, and then it's going to immediately close afterwards. So basically what we did is we forced Algorand to get it to run, even though we actually didn't give it any money. We just had to prove that we had a minimum balance to get it to run. And this is kind of an interesting thing because, you could do this arbitrarily much and get lots of programs to run, even though you actually only had one minimum balance. Okay, so if we go back and we look at the approval code, basically what it does is, remember, the escrow account says, am I part of a transaction with the application? But it doesn't know any logic. The application, it also is not going to have any logic either. All it's going to do is it's going to say, well, is that second thing one of the messages that I know about? Because I know about message 1, I know about message 2, and I know about message 3, and I don't know anything else. Now, why is it number 2? It's number 2 because 1 is the application. Well, sorry, 0 is the application. 1 is giving this message a minimum balance so it could run, and then 2 is this message closing out to the original sender. So that's what, and it needs to be in that order because there's a ticket on this, but basically, like, Algorand supports atomic transaction groups, but they basically have to be executed in order. So like, it can't be the case that at the end of the program, like, what am I trying to say? If like something in the beginning transfers away 5, then it has to have 5 at the start of that transaction. It's not that at the end of the entire transaction group things are balanced. It actually, they have to be there from the beginning. So basically you can't have a circular system where the first transaction is only allowed because it receives from the last ones. Okay. Now the other thing that's going to happen is that application, why does it exist? The only reason it exists is to save state. And so what it's going to do is that we're going to have a few state variables. And these state variables basically are that previous state thing that I mentioned before. And it's the previous state, and it is another one, which is what the time of the last message was. So those are the only 2 things that are going to be in the state, just those 2 things. So basically what we do is we just say, well, let's go look at that state and let's make sure that it is equal to the application call's first argument. What is the application call's first argument? This is why we need that simulation. Because we know what that's supposed to be because we computed it right here. So we know what that is. So we're basically going to say, we're going to send the message and just going to say, here's what I think your previous state is. And then the application is going to check, aha, yep, that's really it. And then we're also going to send along what we think the time is. Then what's going to happen is that we don't check anything else. We don't check anything. All we do is we verify that the state is accurate, that it's one of our friends, the 3 handlers, and then we just trust that the handler does everything else. And so that means that we don't have the logic to know how to update our state. Since we don't have the logic to know how to update our state, that means that we have to have it given to us. And the way that we have it given to us is it's one of the arguments. It's this next state argument. And so the next state argument basically says, okay, well, what I'm going to do is I'm going to look at that first argument and just put that into the global state. So this is me trusting that the handler has checked that the next state is valid, saving it and just plopping it in. We also record what the last round was. And then what these 2 things do is they're recording other things. Basically, they're recording, is the program over? Is it a halt? And then the other ones is having to do with the views. Views are basically a way of saving extra variables that are not digested. They're just in the clear so that other people can come and look at the various aspects of the state of your program. So a classic example of this would be like, you want to know who the current owner of an NFT is. The actual application doesn't store any of this information in the clear. It just holds a digest. And so you need to hold some things in the clear so you can look at them. Okay, so that was just, compiling 4. So we've now, we figured out what application we're going to be. We're going to be 76. So then we go off and compile everything. Now that we've compiled everything, now what we can do is we can update the application to be this code. So this is the only time that approval 0 gets run. And approval 0, all it does is it just says, are you me? You know what I mean? Is it from me? And is it the only thing that's there? Because nothing else is allowed. Then what we also do is we also give a minimum balance to the escrow contract. And the reason we do this is because in the future, the escrow account is going to receive funds. And when it receives funds, it has to, it has to make sure that that it can send them away. You know what I mean? Because like if in the normal operation of the program, it never receives enough to get over the minimum balance, and it can't actually have transactions leave. So we basically have to send it some money, and this money is going to be returned at the end of the program to the deployer. So anyway, so we then, send those off, and then we record what round it was created. And then this information about what the application ID is, what round it was created, and who deployed it, those things are going to be recorded in the get info field of a reach program, because other people are going to need to know those so that they can compile the same backend that they already have, because they have this code, so that they can go see if it really is the same. So they can take that application ID, take the deployer, inject them in, do the same compilation that we just did, and then go check and see if the code really is that code. And they're going to need to know the creation round because they want to know when this happened. So they need to be able to go back and say, did it really get created at this time? And the reason that it's important to know that it really got created at that time, because remember, we need to know one of the variables is what was the last time that something happened. And so that's why you need to know the creation round. Okay, so that's just like the creation process. So let's now like look at the actual program, how it works. So here's the the actual compiler, and it's 1,400 lines. Hold on. So JJ has a question. Does that include any fees it might need to spend, or must fees be provided by the steps of the program if you want an escrow account to pay you? Yep, fees are going to be part of everything. So every program is going to send fees to all these steps. So basically that means that users pay for the fees associated with everything else. So like, remember how I said that one of the things that you're going to do when you run a step is that you're going to give it a minimum balance so it can even run. You're actually going to give it a minimum balance plus a fee so that it can now, it needs the minimum balance to execute, and it needs the fee so it can have a transaction away from it. So what that means is that you essentially are transferring it, what was that, like 1.011 algos, where the 0.1 comes back to you immediately because it's gonna close out a discount, and then the other 001, that is the fee that got charged for it doing a zero transfer to you. So that's how we make it run. And so yeah, so all the fees are going to happen as we go, and that includes also the fees that go, like if a step has an escrow account, like suppose that one of the steps is that like Bob does something where the escrow account pays Alice. What's going to happen is that Bob is going to pay the fee to get the handler to run, and he's going to pay a fee to get the escrow to be able to output a message from the escrow to Alice. And so Bob is going to pay for that. And you can kind of think of that as being like gas on Ethereum. So like people are comfortable with the idea on Ethereum that you pay stuff to make the program run. And so that includes all these fees. And so this is, of course, why, all these different things that you're doing. This is, of course, why when you run a reach program on Algorand, AlgoSigner pops up 7 messages. So you got to sign every single one of them, because every logical step can turn into many transactions. I can show you an example later where I think it's like 15 transactions for one step of the program. That just kind of a fast forward. What those 15 steps are is that it actually has to opt in the escrow account for an asset, for an ASA, opt it in for another one, because this one is like an atomic swap. So it opts it in for 2 ASAs, then it does the transfer, and then it has to close out the membership of the ASA, close out the membership of the other ASA, then close out the escrow account. So basically there's like 5 of these like meaningless ones where it opts in and then opts everything out. And so that, of course, is a lot of fees because you got to pay for all of those things. Okay, so anyways, so we're in the compiler. So there's a few things that we do two Algorand programs before we even, yeah, they are signed by the logic sig, so there's no pop-up. So I was a little bit, there's not going to be 15 pop-ups, but you're going to have to pay, you're going to be paying money. You're going to be generating a call to the application, which you're going to sign. You're going to be generating a pay transaction to the handler, which you're going to sign, and you're going to generate another one to the escrow account. So basically every time you're going to sign at least 3, and you might, yeah, so 3 pop-ups for that one. I think it's going to be always at least 3. There might be situations where you can get more, but I think it's at least 3 all the time. Okay, there's a few things that we do to reach programs before we even get to like the Algorand specific parts, which is that we do what's called de-jumping. Basically, what de-jumping does is, if we look at that program, then actually this program doesn't do it. But in the AST, I talked about how there are loops. So basically, one of the things that can happen is that you can have an Algorand step that enters a loop. And then when it enters the loop, then inside there, maybe it enters another loop. And essentially what we do is we just inline all of that stuff. It's not actually necessary to do this. It's more like a code organization thing. I basically made it so that the Algorand part, whenever it sees a loop, it kind of ignores it because it knows that the code has already been inlined. I used to try to do something fancy where I like switch the compilation context and like start compiling there. But basically I got all sorts of error. It was complicated to do right. And then there were also is like leaving optimizations on the table. So essentially now what I do is I flatten it and I inline everything. And you could do the same thing on Solidity if you wanted. But I guess I'm kind of trusting, maybe incorrectly, that Solidity makes use of similar optimizations. But also the other thing is that on Solidity, there's an incentive to have your whole program there so that the code size is smaller. But on Algorand, there's actually you can't do that because you can't fit everything in the application anyways. So you got to use all these little side handlers. So since you're going to use all these side handlers, you might as well inline the code and remove the function calls so that you can expose optimization opportunities. In the future, when we have TL4, probably we won't do this. We'll probably compile it so that everything's all right there. And then we'll basically be conserving code size by discovering functions. Whereas right now, by removing function calls, it basically allows us to inline variables. And so anyway, so that's what's going on here. So we de-jump. Then the next thing that we do is we actually unroll all the loops in the program. And this is really bad because it drastically blows up the program. So basically, if you write a program with Reach that has a loop, it is going to be unrolled because there are no backward jumps on Algorand. And once that happens, probably it's going to be too big anyways. But we try. There are quite a few programs that do work. But yeah. Then once we do the de-jumping and the unrolling, well, then we're going to optimize again because we want to, we've now exposed structure of the code. So maybe there are useless variables that aren't there, that aren't needed. So we run the optimizer. And optimization basically has a downward pass and an upward pass. And they're 2 separate steps. So one is called optimize and one is called add counts. Kind of a weird name for an optimization, but this is basically optimize down and this is optimize up. In compilation, basically all compilers are either, they either do top-down algorithms, bottom-up algorithms, fixed point algorithms, or they do purely local transformations. And like unroll loops is a good example of a downward one. De-jump is a downward one. Optimize is downward. Add counts is an up one. Yeah. So you can always take anything and just mash it into a fixed point algorithm, but I like to have, I kind of have like a nano pass structure for this. Okay, so when we can now go into the program, assuming that there are no loops and assuming that there are no jumps, and we'll go into actually compiling the algo code. So that's this. Okay, so basically what I've done is I've written a Haskell monad where I can write inline teal code, and this gets recorded by the implicit state of the Haskell program, and I can, at the end of it, say, so what code did I generate? and then I can just see the list of code. And so basically I can run Haskell programs, and they basically are just injecting code into this global list. And it can do stuff like, yeah. So anyways, so there's a lot of details. So I'm really going to kind of talk about the high level parts. So like, here's kind of a simple example. This is that app 0 program. So this right here is the approval program 0. And basically, I've just written it out by hand. So I say, check to make sure that we're an app transaction, check to make sure that we're not rekeying, check to make sure that the sender is right, check to make sure that the application ID, if it's zero, then that means that it's being created right now. And so that means it will go to the initialization code, which is down here, where we just make sure that the next thing is a no up, and then we'll be done. And then if it's not that, then we'll actually say, well, there are two things. Are we updating the application? And then let's set the state. Now here is kind of an example of where we can write some things that are kind of nice, where I have this helper where we're saying, okay, I want to put this key right here, and here's the code that's going to produce the value that we put in. And C state means compile a state. Here we're going to compile where we want the round. Here we're going to compile a literal, which is the bytes empty, and then here we're going to record the halt key. You can kind of think of this little language as sort of being like what you would do if you were trying to make something like PyTeal, but you made it in Haskell. You'd kind of do something like this, and that's kind of what's going on. And it has all these little helpers. For the application, we do something kind of similar, where we say, okay, let's make sure that we're an application. Let's make sure that everyone is here. We'll check the transaction thing, and then we'll update the state. And then here it says, we're going to insert in all the checks for all of the handlers. So this hchecks thing right here, this came because we went through all of the handlers and we outputted this little program right here. And this little program checks to see whether this handler is one of the right ones. So it says, well, is the sender me? And then is it equal? And then we'll just OR all those together. So we OR them all together, and that's what this checks thing is right here. Checks. And we start off with false. Now this false, by the way, didn't show up in the program, I don't think. I'm not sure. Because we actually have a peephole optimizer that's going to look at the teal code that we generate and find transformations that we can do. So it can do stuff like realizing that you're ORing something that you don't need to, and we'll get rid of that. So anyway, so then, that's just that part. Clearing is simple. The contract, the escrow contract says, we don't check anything. And this is kind of the most boring part. We want to go to the more exciting part. This is where we actually compile the handlers. And they're all in here. And I feel like I need to describe a little bit more some of the structure that things are going to do. So in Teal, there are scratch slots and there are stack locations. So that means that if you want to save a variable for later, one way to do that is to push it on the stack and then know that that location is some ways back. In a normal compilation to a stack compiler, you have the ability to do what's called a dig, where you look back at a certain number of stack locations. And normally you can look back at an arbitrary number. This is the way that it works on the JVM. On the EVM, you can only look back 16, and that's where this 16 local variable error comes from. But on Teal, and JJ added something recently to make it so this is not a problem, but when I designed it, it was this way. You actually couldn't look back at anything. And so since you couldn't look back at anything, essentially that means that the stack was not really a viable way to store things. Basically, it was just a way to encode the structure of your program. So what Reach does is it treats the 256 scratch locations basically as like a stack. So what it does is it allocates global variables starting at the bottom, the last one, and it allocates local variables starting from the top one, and they grow towards each other. And so basically, at certain static parts of the program, the locations at the front will be pegged to certain values. So for instance, like if you have like a branching structure, then like in the beginning, maybe you would allocate a local variable, which means that you're going to claim scratch location 0. And then the next time someone tries to do that, it's going to get stack location 1. But then if that code returns, and when I say return, I mean return inside of the compiler, basically, because there's like a static stack in the compiler, then now it can get that location again, but it can't get 0. So essentially, I have this like dual stack thing going on. The other thing, though, is that many times in reach programs, you don't actually need to remember things because it's only used once. Or maybe you know that it's small enough that why bother storing it in something, because you know that, like, as an example, if it's the number 5, even if the number 5 is used all over the program, loading a stack location costs 2 bytes, plus the 2 bytes to install it before, but actually just embedding int5 in the program also costs 2 bytes, and maybe it can cost less because that constant might be optimized away. So for certain small values, it doesn't actually store them in these local variables. It just remembers that this variable is this particular thing, and it will just copy it all over the place. And it can, and of course, only do this for things that are not mutated. So anyways, so, we have some, nice code to construct everything, do all the checks that I kind of walked through before. Probably the most interesting thing is that as we're running, we're going to be noticing that other transactions had to exist. So for instance, when we get to this point in the check pay, that means that, aha, there must have been another transaction that transferred money into the escrow. So I got to check that. And so essentially what's going to happen is that we're going to remember how many of those are. And at the very end of running the program, we're going to say, aha, well, now I know how many things there should have been. So I can statically say, the group size must be this, so there's no extra ones. And then I can go through and uniformly check all of their like timeouts to make sure that they're valid. So let's look at how we actually compile things. We're scrolling past stuff like where we've hard-coded in what arguments are in particular locations and what the types of those arguments are, and a little helper function to read the arguments, and what order the transactions occur in, and what the keys are called. I foolishly thought that I would be saving space by giving them one letter variables, but it turns out that actually you pay for the entire space that it could possibly take. So this was dumb, but it's nice to name it key halts. Who cares if it's H? And then here are the template variables. Okay, so let's look at something like where we see actual compilation happening. So if you're doing a common thing, you compile the common thing, and it gets to see what its continuation is. If we have an if statement, we compile the conditional, we generate a new label for the false, we jump on a 0, and then we generate a fresh label, a fresh state to record what things were copied for the true code. Here's the false code, and then we do the same thing for the false branch. So this is just like, this is just assembly authoring, nothing special here. Same with switches. We know that jumps won't happen because we did djump. When we're done, what we do is we check to make sure we got the right view argument. We check to make sure we got the right next state argument. We check to make sure that the halt argument is true or false, depending on whether this is done or not. And then we finalize, where finalize basically means we record all of the last stuff. Where finalize does stuff like closing out all of the accounts that you needed to do. Yeah, stuff like that. Then if we look at compiling individual things, so if something is run for an effect, then we just run it and we continue. If it's used once and it's small, then we'll save it. If it's used many times, but it's still small, then we'll save it. Otherwise, we'll actually allocate a stack location for it. And when I say stack, I mean our fake stack, a scratch slot. if we have a map, then this map actually, it can't happen because we've done loop unrolling, but I've actually already implemented the code that would allow me to use backward jumps if they were in teal. So basically you can see here untested code for how we would do backward jumps if they were allowed. When you do reach has variables, which are basically like mutable things. And so we allocate a scratch slot for them to store the variable name. And then we also have a variable location where that's at the end. You can set them by storing into that slot. A local if is compiled just like the other one, except that we can't use the same code exactly because there has to be an explicit join point. Because the earlier version of if that we saw, the true and the false actually contain the end of the program, but a local if is one that joins again. So you have to branch out and then come back in. Local switches are similar. And then map reduces and onlys, these are things that are statically, that are impossible because of the way that reach compiles. If we look at something like a transfer, so this do transfer function, it gets called by some of these things up here. Let me go up here. So these are like the common things that can happen. So for instance, like you can call a primitive. This is where like addition happens. You can reference an array. You can set an array. Setting an array is extremely painful because basically what we need to do is we need to figure out where this. And so how do you set something? Well, what you want to do is you just want to like, modify the memory that you're going to change starts, copy everything before that, copy everything after it, create your new value, and then concatenate them together. And you kind of got to concatenate them in kind of a weird order because you want to concatenate these ones first and then those ones. And, you have to like duplicate the substring argument. And so basically there's some optimization here to when it's safe to, when the thing that you're going to be inserting in is small. And so it turns out that like this code path, even though it looks like it's longer, is actually fewer bytes. So, I mean, like I've done some things where like I have a program, I compile a program, and it's literally 1,020 bytes long. And I'm like, I got to get 20 bytes out of this program. And so that's why I go down and I figure out stuff like this. But okay, well, maybe I can look for this very particular situation and change that. And it also does things like discovering when it can do a substring 3 versus a substring. That's like whether the substring bytes are embedded in the opcode or whether they occur on the stack. Because if they occur on the stack, that means that it uses more space. What's another fun thing? Okay, so transfers are probably the most interesting ones. So basically what these things are is, so this code, a transfer means that you're paying somebody. A token initialization means that you are receiving a token for the first time because we don't know beforehand what tokens, a token is an ASA, what ASAs a given reach program is going to be involved in. So, and it can discover that, like you can send it a message and say, all right, you're involved with this token. And so that means that it now has to discover, you should opt me into that token. So this essentially says that you are going to opt me in for this. So there are different, what are called transfer kinds. So there's, I'm sending something, I'm initializing a token, or you're sending it to me. And if you send it to me, well, I need to know whether I'm receiving a token, in which case it's an AXfer, or whether I'm receiving a normal algos, which is a pay. So basically this all deals with this. And one of the other things that we need to remember is like, there are all these fees. So the code will say something like, you had better have paid me 0, but actually you had to pay me more than 0 because you had to pay me the fee so that I even ran. So basically I have to know how much the fee is going to be. And the fee is of course variable across the program. So one of the things that happens is that the clients, they figure out what the fee is going to be. Well, because they construct the whole transaction group and then they send the fee in, and then you just make sure that that fee amount you kind of like subtract from every time you go look at the amount. And this, this whole thing about when you see a transaction, the way that it works is we statically allocate a transaction number. So we basically say, give me a transaction number. And it's kind of like the stack locations, the scratch locations where we say, oh, give me a transaction. And we'll be like, okay, this one is transaction number 8. This one's transaction number 9. And then we're going to now check all the different attributes of that. And now we've remembered which one it is. So that basically means that every path through the program, like one path through the program might have 5 transactions, and another path through the program might have 6 transactions. So that means that like if they share a common prefix, the checking for that code will only happen once. But it could be the case that there's just a branch, and on one side there's these 5 transactions, on the other side there are these 6, and they're just totally different. And so there can actually be lots of code that gets generated for transactions because we have to copy all this stuff. This right here, this do transfer function, this would basically be, if we had functions in Teal, this would be a function that would be on the runtime. But because we don't have functions, it becomes a compile time function where we're basically inserting in this template of code all the time. What other things that are interesting? Maybe, there's all sorts of optimizations to discover nots and ors and not ands and not ors, and when go to a select, because Reach doesn't actually record ands and ors or anything like that. So basically there's all these patterns to identify particular kinds of things, and this is all for code size, to try to get the code smaller. We also have, as I mentioned, the peephole optimizer. So it can do stuff like, you did a B2I and then an I2B, so let's just get rid of that. You did an I2B that we knew was looking for a bool, and you did a substring where you're looking at the last thing, so we can actually just remove this from the program because we know that that number was always a bool. That's a pretty specific peephole optimization. Another one is like, we see that you're doing a substring and then another substring, so we can actually figure out that you should have done a bigger substring between them. So this is kind of crazy, but we do stuff like that to make it fit. Now, I just want to show you one last thing, which is like, how do we actually send one of these transactions? There's all this stuff to construct them. So now we're going over here, and let's do a send. So how a send works is that we get called with what the arguments the user wants to send to the program, what function they want to call, and how much they want to pay. And so what we do is we go off and we look up that handler. So we say, okay, you're looking for number 1. Okay, so let's go look up that logic signature. And then we'll construct input to the simulator. So then we'll go do the simulation. And that simulation is going to tell us, okay, this program is going to halt. Here are all the transactions that there should be. Here's the way that the view should change. Then what we can go do is we can go actually construct all of the right objects. So the simulation, it sees those same things, the in transactions, the out ones, the initializations, and it records them for us. So what we do is we construct transfer transactions, and we remember them, and we total up what the total fee is going to be, stuff like that. So then once we compute that, we then say, okay, well, here's what the actual arguments are going to be. I can use the simulation to figure out what the previous state was. I can use the simulation to figure out the next time. I can look at the view. I can know if it was a halt. I can know what fees there were. I know what the last round was. And then here are the actual arguments to the function. Then I go encode all those as, uint arrays. Then I go off and I say, okay, well, if this is over, then I'll delete the program. Otherwise, it's a no-op, because that's something that goes on. We detect when the program is over, and it allows the program, well, it actually enforces the program to delete the application. And that also closes out all the accounts. We then generate that transaction. We generate the one that comes from the handler. That's the one that gets the handler to run. And then we transfer money to the handler so they can, which is its fee plus its minimum balance. Then now we have all these transactions. We go assign them a group number. We go off and we sign them all. Once we sign them all, then we assemble them together and we send that transaction group. And then if it works, then we go off and do a receive. How does a receive work? A receive goes up and looks at the handler that it expects to receive from, because that's how it knows what logic signature it should be looking for, and then knows when it's looking for things. And it generates a query to the indexer that says, all right, I'm waiting for a transaction where this handler is sending a message. You might think that we're going to be looking at the application, but we're not, because we need to know what method is being called. And there's no way in the indexer to check out the arguments to applications. So we couldn't like have that be an argument to the application. So instead we have to do is we have to look for, there's money coming out of this logic signature. And so that means that it must have been called, because we know what that logic signature code is. So we look for that, and this tells us when that handler call happened. Once we know when that handler call happened, we now know what round we should look for an application call in. We know that only one application call can ever happen inside of a round, and this is going to be a constraint that could be broken in the future. So now we know that we're looking for, in this round, this application was called, so we can look at it, and then now we know what the application was, and then we can go just read off what the arguments were. And we look at those arguments, and now that means that those arguments that got sent, in the original program, the request size, the information, those arguments have been checked by our program. And that's why you want dApps. You want dApps so that these arguments can be checked by code. All that other stuff, we actually don't really care about that. Like the user, what they care about is they want to share request and have everybody else know that a whole bunch of checks were made on it. And so really the thing that really matters to the user is this line right here, where we figure out what the arguments were, and we take those arguments and we send them back to the reach program so that the reach program can then automatically process them. So it's 5:01 now. That's all I've got to say. There were a few questions beforehand, but any
you
other
nailed
questions?
it, Jay. So I have a question, and this is actually questions for the Algorand folk, and maybe the answer is I don't know yet. And now that you guys see how Jay built the actual compiler, it was actually mostly me, but is there anything that you guys can think that could be done differently with the teal language to not have to do some of these jumps? And that is, I guess, open question.
They can answer, but we've talked a lot about changes that can happen in the future of teal, and I've sort of given them lots of ideas, but maybe now that they've seen them, maybe they can think of more ideas that didn't occur to me.
So, like I said, you knew about the compiler and how everything works, and maybe they're like, because there's a few things like with your optimizations and things like that, where, because I can remember the things that you've asked, but there's things that you hit on in the actual compiler that I don't remember was a request specifically, and wonder if there's any question.
Yeah. Yep. So assert equal is really common. So in my code, I use assert equal all the time. And so if I had assert equal, yeah, I would save 1 byte. That would be good.
There's been times I've seen you're like, I needed to get 1 byte. So
yeah. I mean, it is absolutely the case. So just as an example, so just 2 nights ago, I was optimizing a program and I got it down to 1,006 bytes. So I had to find 6 bytes. I eventually figured out a way to get 6 bytes, but if I had 1 byte less for every equal assert, then those 6 bytes would have been there.
This is right. I don't know much about this stuff, obviously, but you did mention like if Algorand had functions, is that a hard thing to do?
My understanding is that JJ already has a branch that adds this, so this is something that's definitely going to be in
great job, JJ.
The thing though is that just having functions is not necessarily everything, because you would have to, a function's only useful if all of the arguments can come from the stack. So what I mean by that is like this one right here, like GTX 0 application, like that 0 right there would have to be able to come from the stack. I believe that JJ actually added this, so that's not really an issue. Yeah. Now, JJ asks, I'm curious how interoperable a reach program can be. Can you easily document how to call a reach contract without using reach? There is no existing standard for how to call any program on Algorand. I suppose that you could say something like make an application transaction with these things, but because of the way that reach offloads the code onto these sets of handlers, these sets of other logic signatures, I think that it would be disingenuous to call that an ABI specification, because essentially means that you need to know what the code is. So I think that I would say that no, you can't easily document how to call a reach contract without using reach. But if we could get everything inside of the application code, then we wouldn't need to do that part. And since we wouldn't need to do that part, it would be quite straightforward to come up with an ABI for Algorand apps that would be very sensible. And we would just document what that was. But right now, I kind of feel like the answer is no. Even though it's technically possible.
Yeah, but okay, but potentially we should in the future be able to fit everything in a single application.
Yeah, because basically, once we don't have to offload the code, then the interface doesn't have to include the code as part of it. Because kind of the way that I think about it is that something is only an interface if it means that you don't need to know what the code is. And so since the way that we compile means that you need to know that when you call application 71, you also include a call to this logic signature, which is code, then that means that any specification of how to call a reach program includes the code.
So we'd love more space.
Yeah. And you would have had to, you would have to, that's another way that you would need to have the code, because you would need to have run the simulation to even provide the right arguments. But remember, the only reason we do that is because the stateless contract doesn't have a way to look at the state, and the stateful program doesn't have enough space to do the other one. So if we could get everything to the application, we would just delete all the simulation stuff. Asterisks, we need to be able to know what the transactions are going to be. So basically, kind of all of these things go together. If we can output transactions, then we don't need to simulate. And if we can get everything in the application, then we don't need to simulate. But if we only had more space, you would still need to run a simulation to know what other transactions should be there. I mean, of course, no matter what, the specification language, like the ABI spec for Algorand, is going to say stuff like, you call the application and you had better also have transferred money to this person, and et cetera. You know what I mean? Because that's like part of the effects, right? So you would say, I'm calling this function and I'm transferring this money. Like if we were to imagine, like a C-like language for describing Algorand transactions. Let me just kind of open up something real fast. It would say something like, there's a function, it's called f, you give it an integer, and then it is going to return another integer, and it's going to expect there to be, a transaction, a pay transaction from, A to me, or A to B, or something like that. And it's going to expect, an AXFR transaction, something like this. Maybe what you would do is you would say something like, there's going to be an address named A, and then that address is going to have to show up right here. It's not really clear what you would do. Maybe in the minimum, all you would do is you would say something like, these are the things that are expected to be received to the escrow account. So we would imagine that every Algorand app would have an escrow account, or would be an escrow account, and it would say something like, I expect to receive a pay, and then I expect to receive an XFR, and then I expect to receive another XFR. And then that means that I'm not gonna specify the details of how much these are, because that's kind of the details of this code, but I at least have to tell you what order they're supposed to be in. Something like that would be what an ABI spec for for Algorand. Okay. Oh man, I clicked this wrong thing. Okay, so Dan says, can you briefly comment on verify contract and how Bob can be sure that each handler that gets called is the code he expects? I presume it's related to how each handler's address is computable from the handler code, and all handler addresses are embedded in the code which Bob inspects on the chain. Exactly. So every time you call attach, attach is what the reach standard library thing is that like takes the contract information and loads it. So one of the first things that you do is you go off and you call verify contract. So you make sure that this contract info you were given really is the one for this binary. So what verify contract does is it says, all right, let's get the client. Let's go look up this application. Let's look at its parameters. Let's go to the indexer. Let's look at when it was created. And let's see, and we'll make sure that when it was created, it really was created at that round, because we're seeing, is there a call to the application in that round? And let's make sure that we can see that the approval program really is what we expect the approval program to be. And its clear really is the clear, and its deployer really is the deployer. And that first transaction really set all those things up when it was supposed to be. You know, we checked to make sure that there really was an update on that line. And yeah, so since this approval program embeds the hashes of the handlers and the contract identity, that means that you know it can only run with those programs because you are the one that did the substitution. What you did is you ran that function compile for. So you ran compile for locally before you verified anything. So you know what you're looking for. Now, we were just talking a moment ago about how a non-reach program would contact a reach program. The only way that it should safely do this is if it also does this contract verification step. So the only way to do contract verification is to check the code. So, and that's kind of a thing that happens already on Ethereum. I kind of, by the way, maybe I'm a bit of an imperialist in this way, but I kind of think that like Ethereum is the normal, and so we always want to compare what happens in the normal world, what happens in the Algorand world. In the future, hopefully, this is not the case. Yeah. So anyway, so you would like to do that, and that means that you would have to actually have the code. You would go look at the app, you would download its stuff, and you would check it out. Yeah. Okay, so JJ says, does the compiler need access to an indexer to get IDs? If yes, is there any other reason? When you say compiler, you mean this compile for function? No, it does not need the indexer at all. The verifier uses the indexer to check that it was made in the correct round, because you need that archival information. But if you were willing to not check what round it was made in, then you would only need a current node, because you just want to look at the code to see if the code is right. You would know that the round was wrong. So kind of like, what's the job of verify contract? On one hand, its job is to check that you can trust this code. And the other thing that it's doing is it's saying, like, is the call that you're going to make going to fail? And you don't need to know that it was made in that round to know that you should trust it. But if you trust the code, but you have the round wrong, then your message is going to fail. And so we only need the indexer for that second check, not the first check. So yeah, it wouldn't need that. Why do you need this round? We need the compiler stores what round it is. So it can check timeouts. So one of the features of Reach is that, let me open up a program that does this. So you can do something where you can say, like, Alice is going to pay into the escrow account, and then Bob is going to pay in. But if he doesn't reply in a certain amount of time, then Alice can come in and take back all of the money. So we need to have a way of knowing So we need to have a way of knowing how much time has gone past. Now, this is like part of the Reach compiler, because it really knows about this whole application thing. This whole timeout thing. And the reason why is kind of another weird detail. Remember that we need to simulate running the Algorand program. And since we need to simulate running the Algorand program, that means that we need to, if the program could look at the current round, then we would need to not only simulate the running of the program, but we'd also need to guess correctly what round it's going to run in. So actually, the compiler goes out of its way to make sure that the Reach program never can actually look at the round. You can only see what time it is after the transaction has already happened. And this is actually like, this flows way back into the Reach program. There's a function in Reach that's called last consensus time, and it tells you when did the last commit happen. And people always ask, why isn't there a this consensus time? And the reason why is because on Algorand, you couldn't get it. Of course, you could technically look at the round in teal code. There's nothing wrong with looking at it, but the problem is that we need to simulate it. So we would have to make sure that the code doesn't look at it, because if it did, our simulation is going to be wrong, because we're not going to guess the round correctly. So because of that, the state that is stored in the global thing is different than those sort of saved variables. Like those saved variables include the time, but that one thing is explicitly removed. Okay, that's why it's separate. So the time is stored in the global state, but it's separate from this whole state thing. Now, why do you need to know what the creation round is, and why can't you check it? Because the indexer doesn't let you look at older application states. So the indexer indexes transactions. It does not index past versions of application state. So there's no way on Algorand right now to answer the question, what was the global state of this application in this round? That's just not, the indexer doesn't keep track of that. Or at least it didn't when I wrote this. It's possible that it's changed.
Is this something that if there was a change to how Algorand worked, it would be a more elegant, clean way that we could do it with Reach?
If we could get rid of the simulation thing, then we would expose to Reach programmers a way to look at the actual time. Okay, so what Furby says is, what I'm a bit confused about is, since the application does not use the creation time, why does the JS need it? The reason why is because before the program starts, you can look at last consensus time. And because you can look at last consensus time, you can make it so that the very first message has a timeout. And you might say, how could there be a very first message at the timeout? Well, the very first message could be a race between A and B. And if they don't answer, then there's a timeout, and then C will do something. So that timeout thing can happen on the very first message. And all timeouts are relative to something. And so they're relative to the creation time. Tangential question. Is the indexer required to observe views? No, views are immediate things. So views are, what is the state right now? And so that queries the algod node to say, what is the global schema? And it can just look at it. So the get views function, what it does is it says, go look at the application state, look at its parameter, look at its global state. It knows to look at dg == which is v, and then it will then decode them, and then it knows, and then the way that a view is stored is it says, I'm view number 4, and then since I'm view number 4, then I can go look up what the rest of the bytes are supposed to mean, and then I can decode those. Now, Dan says we could conceivably expose creation round as a view. We could also just expose creation round as a global schema. But the reason we don't want to do that is because we want to use as little space as possible. Because everything about this is to conserve space in every way possible. So if we don't need to keep track of it, we don't keep track of it. So the creation round would only be needed on the very first message, and then it's not needed anymore. So that's why we don't keep track of it in the global schema. Because global schema means saving it forever, you know, and you have to pay for global schema cells. So we want that to be as small as possible.
Maybe someday, Dan.
Yeah, maybe someday we'll have more space. Certainly, and you know, the thing that's funny is that creation round, for instance, like we're actually already paying for space like that we're not using, because we have to pay for the entire length of a key, even though we only use one byte. And of course, I've told JJ about this a million times. I don't even want to have keys. I just want to have address 0, you know, address 8, etc.
I personally am very excited who we have in the room right now.
Yeah.
Fabrice, Shai, JJ.
Yeah, we've got the
Russ,
all-star cast.
Ryan, yeah. All of you guys get to actually really see the fun stuff that the hoops.
Yeah.
Like I can't tell you guys how many times like Chris Nevers or Dan was like, or got new file done. It's 1,200 bytes or what have you. And then I say, there's no way we can cut this down again. And Jay yells at me and said, you had no faith, and shows me that he cut it down to like whatever it needs to be.
Yeah. So like this program right here is an auction for an atomic swap. So what it does is you like propose one side of a trade. So you say, I want to trade 1 USD for wrapped Bitcoin. Send me your best bids. And then it will resolve that. And so I'm only showing you the compilation output. But you know, this program ends up having 8 different steps. And the reason it has all these different steps is because basically because each one is like a different control flow. So like one is, you know, you're saying that I'm initializing it. So the escrow account has to receive USDC, and it has to receive wrapped Bitcoin. Then you then start recording that you want to have an auction. And then you start accepting bids. And when you accept bids, you have to like, the escrow like will actually force you to send in what your bid is. And then because you had to send it in, that means that you might also have to send back the previous winner's bid when you outbidded them. And then when we're at the end, we then actually do the final transaction where we send, okay, well, you know, you, the bidder, you got your asset, and then the other things, they go to the owner, and then we have to like close out all of the accounts. And so like this program right here, like this step, this one's interesting because notice that it like, this check pay is a transaction, this check pay is a transaction, this transfer is a transaction. And then there's an if statement. So on one side, we don't have transfers, but on the other side, we have 1, 2, 3 transactions. So this one right here, this program, when it goes down this path, that means that there has to be 6 extra transactions in addition to those other 3 that I told you about. So this program right here has at least 9 transactions in it when you run it on Algorand. And it kind of just emerges organically. So like this program right here, when Chris originally wrote it, Nevers, not Chris Swinner.
I wrote it in my head.
When Nevers wrote it, the compilation was literally like 26,000, 2,600 bytes. So 2,600 bytes for this step right here. This step right here was originally 26,000. And the code, this output would have been different because I did some optimizations elsewhere. So basically I implemented new kinds of optimizations. I did things like, you know, switching if statements when you see that there's a not, tracking more variables. Nevers actually did an amazing optimization that made it so we could expose more pieces of the output of a loop. And we got this down to like 600 bytes. So, you know, you might hear me complain, oh, give me more space, give me more space. And you think I'm just whining and I'm not trying hard. I'm trying really hard, you know, to get good space. Yeah, okay, so JJ says it feels as though looping and or functions will have a really big space saving effect. Do you have an idea how big programs will be? I think that those will be big. So as I mentioned, like the very first thing I'm going to do is I'm going to write a function that is transfer. And transfer is a huge amount of code. It's just very big code. See you later, Ryan. It's just a lot of code to do that transfer, to check everything. Similarly, every transaction, it kind of like puts something at the end of the program where it like checks all the timeouts because we don't actually know what the timeouts are beforehand. So that would be another thing that would be really nice. So I think that just functions would make big drastic benefits. But the thing is that just having functions, unless I also have dynamic accounting, doesn't matter either, because that's this other thing that we talked about, which is that, you know, if you have a big program, but every path only has 700 bytes, but if you look at the entire program, it's, you know, 10,000. Yeah, awesome, JJ. That's already there. So yeah, so I think functions are going to be a big deal. Looping matters. So like, I'll show you a crazy program. So we have a program that's tic-tac-toe. See you later, Russ. Thanks for coming.
Hey, Russ.
So tic-tac-toe, you might think, of course, there's going to be looping because you're going to have to iterate through the matrix to figure out what you've done. So like, this is the code that gets generated for it. So this is just like one step. Now, what this code is it's checking to see if you have a row, if you have a row and then a column and then an arrow, you know what I mean? Because it's enforcing that the rules of tic-tac-toe are actually played, because it says, well, if the game is over, if the game is not over, then you keep going. But if the game is over, then you figure out who won. And so here's how you figure out who won, and then you transfer the money out. So this code right here, you know, we're gonna identify things inside here that are you know, ors and ands and stuff like that. So if we like look at the actual code, this is number 3. So 3 right here. So this is this program. So that program is 500 lines. That's not crazy, but like this is what it looks like. So, you know, where, you know, getting byte 3, getting byte 2, that would be another thing. Like this right here. So get byte is a byte. And then int 2, that's going to be 2 bytes. So that means getting a byte, like if I could just hard code in, I want byte number 2, you know what I mean? Then that would be quite some space savings. But yeah, so then, you know, we do basically all these things are doing is they're caching the individual cells into storage locations, because we know that load this is shorter than that, basically. So then now when we load these, then we just, you know, compute this giant thing about, okay, is it the right cell? You know, is this a row? Is this, you know, this is just a whole bunch of gobbledygook, which if you were to see it as a program, it would be check row, check row, check row, check column, check column, check column. You know what I mean? So it's quite exciting. But, you know, like it's 500. I worked really hard to get it to this point.
That one was originally really big.
Yeah. One of the other problems with this one was that I actually used to have the arguments to the program be in the logic sig rather than in the application. And that meant that the size of the input then took space away from the code. But Fabrice taught me well and corrected me. And once he corrected me about a security issue, that also had the benefit of freeing up space, because now the arguments are always in the application.
Thank you, Fabrice.
Yeah.
If there's any other space saving things, Fabrice, let us know after seeing this. Excellent. Well, I think that might be everything.
Yeah, I think so too.
And we're already 30 minutes over. So
I'm going to stop sharing, and I'm going to turn off my local recording. And I think we're going to turn off the live stream. And thanks for coming, everyone. It was a pleasure to talk you through this. I think this was one of the most deepest dives that we've done. But I think it's worth it because, you know, the algorithm, like, I just love programming low-level code. It's just so much fun. So